Okay. Rightio. There's something else to be passed around, and that is, okay, if there's some space, please do pass it backwards. All right. Let's pass this around. Pass this around as well. Pass this around as well. Pass this to the back. Yeah, spares, guys. Any spare data sheets? Okay. All right. This is just it helps. It helps when you don't have to flip back and forth between the screens. So that particular data sheet will help us. Okay, so guys, so you should have with you 2 sheets. And by the way, I've sent an announcement out already that there will be a quiz every week. So I think you should be able to calculate that if we had a quiz this week or not, and when the next quiz is supposed to be. All right? Okay, because there's only 3 possibilities per week. So being engineering students, you should be able to do a lot of these sorts of predictions. All right. And when I teach, a lot of the time I depend on the fact that you are engineering students. I don't need to show you each and every little step, because I know from intuition you'll be able to gather, okay, we've done truth table, so this looks like this. So if there's 2 inputs on the truth table, if there's 2 columns on the input side, obviously there's going to be 4 combinations. If there's 4 inputs on the input side, obviously there's going to be 16 combinations. So I depend on all of that, right? Okay, are there any spare? There's 2 sheets which I have circulated. The first sheet is what you call the flip-flop table, right? The flip-flop tables. And we're going to use that heavily, right? You're going to use that heavily, all right? So I've given it to you now. I won't give it to you in the final exam. All right, I'm joking. All right, okay. So you have, I'll just put a few of these in front and a few of those in front. Okay, so I think nobody's sitting beside you. All right. Yeah, so 1 each. Take 1 from each side. Okay. All right. Right, what were we doing, guys? Let's have a look. Okay, and this is our tables is here. Basically, whatever I've given to you, it's already on the Moodle shell, just in case one of your very smart friends did not want to attend today. So it's already on the Moodle shell, but I've just given it to you so that it saves us time rather than flipping back and forth between the screens. All right, so we are now, what have we done so far? We have learned, let's have a look at this table. We have learned the derivation, the proof of 2 of these, right? There are 4 fundamental flip-flops. In fact, there's many other flip-flops available, but these are the 4 traditional flip-flops, okay? The 4 traditional or classical flip-flops, all right? Okay, so we have learned the basics, the fundamentals from scratch, starting from just a single NAND gate, and we have built the SR latch, the SR flip-flop, did the whole thing, the truth table, the analysis table, truth table, characteristic table, excitation table. Then from the SR flip-flop, we modified it, we got the D flip-flop, the whole thing again, the truth table, analysis table, truth table, characteristic table, and then the excitation table. So 2 of them we've done. What we'll do now is, instead of holding us back, because the other 2 will take another 3-4 days, right? And we only have 3 lectures per week. So I'm going to now move forward and show you how to apply these. So up till now, I was doing the fundamentals. How did this thing come about? Now we move to apply. Apply and analyze. All right? Okay. So the problem which we were looking at, was it this one here, guys? Analysis of sequential systems. All right. Okay, let me just put today's date. So we are on, yeah, there's 2 over there. One thing and one exercise sheet and one week 10 lecture 2. Let me just turn on the lights. Oh, the lights are good or not good? And today's date is? Yeah, if anybody walks in, you guys, if anybody walks in, just point them to that. Right? Is that correct? All right. So I think the lights are not good, right? You want something like this? All right, nice. Okay, we are doing the problem. We are doing the problem on, holy cow, what is this? I don't know. Okay, we are doing the problem. So we are doing a problem on analysis of sequential systems. And the problem which we are doing is on page 12 of, what is this, week 9 and 10, the sequential circuits notes, yeah? Okay. Just get him to, yeah. All right. Okay, guys, so this is what we have, all right? Okay, let's flip back, because this particular circuit I don't have with me right now. No, this one. Right. So the step one is we find the equations for all the inputs into the flip-flops and the equations for the output. And we did this yesterday, so we can just copy from yesterday's notes. Okay, so step one is the equations for all inputs going into the flip-flops and for the system output. So let me flip over. So what we learned yesterday was, and we did the derivation yesterday for those of you who attended, and remember, as I've mentioned in my announcement, how many were able to read the announcement or received an announcement just before? By the way, how many of you have got your student email hooked up to your phone? Okay, so, all right, okay. So yeah, about the quiz, So there will be a quiz every week. And, you know, for this week, you can figure out when it will be, right? Because there's only 3 possibilities. Sometimes in the quiz questions, I may even give you gift questions. I may give you something like truth table of AND gate, just to ensure that you're here. Right? So it'll be gift questions. Sometimes I might say, hey, go and fill out the course evaluation survey. Don't show me your survey responses, but fill out the course evaluation survey, right? Or something along those lines. All right? So yeah, so please ensure that you attend each and every lecture. If you don't, then it's really a miss for you. Okay, so we did this yesterday. With this, we looked at this circuit. Firstly, how many flip-flops? 1, 2, 2 flip-flops. Each flip-flop stores 1 bit each. So therefore, this is a 2-bit system. This is a 2-bit system, right? This is a 2-bit system. So that means at any point in time, it is storing 2 bits. Okay. The other point, this is a synchronous system. Why is it synchronous? Look at the clock lines. The clock lines are tied together, so they flip together. Every time there is a clock pulse, the particular system, changes state together. What does the clock do? The clock ensures memory. Remember when we said when clock is 0 in our derivation, we said whenever clock is 0, it's going to automatically go into hold mode or memory mode. So every time there is a clock pulse, every time you have a high going down to low, bang, it saves. Right? It holds the particular thing. So that's why the clock is important. Right, what else did we discuss? There's the 2 flip-flops. 2 flip-flops, that means 2 memories being saved, 2 bits being saved. And another way to word it is, another word we use is, there are 2 states. What do we mean by states? What is the state of flip-flop 1? Well, the state of flip-flop 1 is, what is the, another way to rewrite that question is, so if somebody says, what is the state of flip-flop 1? Another reworded version of that question is, what bit is being stored in flip-flop 1? When we say, what is the state of flip-flop 1, or what is the state of flip-flop C, or flip-flop K, or flip-flop D, it means what is that particular flip-flop storing in its memory at this point in time? Okay, when we say state. And if somebody says, what is the Q star, or what is the Q of D1 or D2? That means what bit is being stored now. What is the DQ star of D1 or D2? That means what is the next state of that. All right? Okay, so the first step, as I've mentioned, is we want to write out. The first step is we want to write out what our particular thing is. All right, so by the way, was it that particular one which we were doing? Okay. D1. What is D1 equal to, guys? D1, all right. Let's trace it once more. We've got to trace, all right. So we're doing a repeat trace from yesterday. That's an AND gate, right? What's coming into this AND gate? Q1. Can you see that Q1 is coming in there? Bang. What about this guy here? Q2. So it's Q1 and Q2. That's a mistake which we made yesterday. D1 is equals to Q1 and Q2. Was it Q2, guys? Let's trace it again. These two. Okay, that fellow there goes in here. That's Q1, definitely. What about this guy here? Q2 bar, right? And if we look at, right, what did we write here yesterday? Somebody told me the wrong answer. Here, somebody gave me the wrong thing, so I'll just say no. This is Q1, Q2 bar, right? Unless we were doing a different problem. I don't recall which problem were we doing. All right, now, so let's correct it straight away. It's good that we are revising, otherwise, okay, let's come back here. And then that's odd with, what's this? Q1 bar and X. Q1 bar and X. right? Now, what is D2 equal to? What is D2? So that's the correct one. So if somebody is watching yesterday's one, they would be really confused. And that's why it's important to come. What is D2 equal to? D2. That's equal to Q1, right? And X. That's equal to X and Q1. What is Z equal to? This is why I gave you the guys that question. Z. Oh man, where does it go? Sorry, Z. Z is over here. We don't need to trace back. Z is Q2 bar. Yeah. So those are our equations. All right, everyone happy? Step 2. Is something called the state table. This is not the truth table, although it is an extension of a truth table. It is an application of a truth table, right? So we're going to do a truth table, but for these flip-flops. D1 is D1 over here. Yes, Q2 bar, yeah? Yeah, okay, sorry, Q2 bar. Thank you. All right, state table. All right, let's draw the state table. Can I fit it in here? Yes, I can. All right. So, check this out. This is very important. It's important that you focus on how I draw the state table. Right? Okay. So we will have, the way we do it is, you have present state. Okay, so we have the system input. System input. I'm going to pull a line over here. You have current state. Okay, so system input, guys. What is system input? Can you give me what is your system input? It'll be X. What are your current states? How many possible current states can you have? Look at the diagram. There's only 2 flip-flops, so there's only 2 possible states. So the current state is Q1, Q2. Sometimes instead of current, people call it present state. Present state, same word, same thing. Then we have in the next block, so I'm going to pull a line over here. I hope it's neat, right? In the next block, you have flip-flop inputs. Flip-flop inputs. Now, how many flip-flops do we have, guys? Let's again look at the picture. How many flip-flops do we have? 2 flip-flops. How many inputs do we have? 2. Only 2 inputs, right? Because there's 2 flip-flops. Each input has got one input each. So therefore 2 inputs. So we can say D1, D2, and then another double line. Then we have, sometimes people call it next. Some people call it future state. And then we have system output. I hope it's visible. Okay, future state. How many flip-flops do we have, guys? 2. What are we going to write over here for future state? Q1 star. Q2 star. Next or future state. System output. Do we have a system output, guys? Yes, and what is our system output? Z. All right. Now, the key part of our table is this 3, right? You treat, so can you see there's a number of sections in our table? There are a number of sections in our table. If you look at it, you have the present, right? System input, right? System input is always going to be present, right? And current state. Then you have the flip-flop inputs. Can you see the double line separated? Then you have next state. Then you have output, system output. Okay, so see my configuration. I want you to take note. Observe how I've structured the table. Because if you structure your table neatly, then things start to roll quickly. If you want, sometimes this column can be placed here, or it can be placed here. The system input line, X, can be, you can do Q1, Q2, then X, or you can do X, Q1, and Q2, right? This side of the table, this first section is, if you think of it along the lines of a truth table, in fact, this is a truth table, except for it's like an extended truth table with multiple sections, yeah? Usually we only used to have 2 sections, input side and output side, if you look at all the problems which you were doing in the past. But over here, we now have 4 sections, all right? Okay, so guys, if you look at the input side, how many columns in our input side? I'm not saying how many inputs, I'm saying how many columns in our input side? 3 columns, right, on our input side. This side, this here is the input side. If you think of this whole table like a big truth table with multiple sections, this here is our input side, okay, right? So we have 3 columns, so therefore how many possible combinations? 8 possible combinations, all right? Let's populate that. 0, 0. Everyone happy how I got that? You have to be on par with me, you have to keep up. Right, the next step. We have some equations. Let's move to the middle section. So this section always the input of any table gets automatically populated, right? Using all the possible combinations. Let's now look at the flip-flop input section. For the flip-flop input section, if you take a good note, if you take a good look, what do we have here? You have the equations. So let's now do that. I'm going to give you guys, so in fact, what 3 columns can we work out of the truth table from the equations? It is equation driven. Yes. All right? So if you look at it, these 3 are equation driven. Okay? D1, D2, and Z are equation driven. So maybe one side of the class does D1, so you guys over here do D1, you guys over here do D2. Everybody from this line over here, there's like an empty row of seats over here, that's like a border. You guys do D2, you guys do D1. Let's populate your table, right? And I'll do Z. Okay, all right. Okay, so guys, for those of you who have just arrived, we did the derivation of the equations yesterday. We are now doing something called the state table. Right? You have to do this step by step. There's a number of steps. Right? So D1, if somebody is wondering what is D1, well, all you do is, what are you going to do? Q1 and Q2 bar, or X and Q1 bar. So you play with these 3 and you get D1. Right? You plug it into the equation, and for every column, every row, you will get an output. Right? Similarly, half of the class will be doing D2, which is slightly easier. Right? And I'll do Z. So Q2 bar. Okay. All right. So we are trying to populate these two columns, D1 column and D2. D1 is based on D1 is based on the D1 equation. D2, there's an equation for D2. And there's an equation for Z. I've done Z because that was easy, just Q2 bar. But whatever Q2 was, you just bar it. Okay, all right, so what do we get? We get yes. Oh, sorry, yeah. I made a mistake over here. That's a big mistake. Last 4 rows is all wrong. That's what I was wondering. How can all this be? There we go. So obviously, this one as well, right? Yeah, okay. Thank you. That's a big mistake because you see, that was a good example of how you can make a mistake. That's because I populated this input side, which is automatic population, right? Automatically we populate according to the number of combinations. And I had written 0, 0, 0, 0 over here. It should have been 4 zeros, right? And what did that? That had an effect over here. And that would have had an effect downstream. So we've done the Z. How did I do Z, right? For those of you who have finished your D2, right? How did I do Z? Basically, Z is equals to Q2 bar. I hope my Q2 bar is correct. Yeah. So basically, it's a flip of Q2 bar. It's an invert of Q2 bar. I mean, it's a Q2 bar is a flip of Q2. So you just flip the bit, right? All this, you flip it and put it there. D2 was, what was D2 equal to, guys? D2 was equals to X and Q1. So all I did was I said, hey, wherever there's a 0, the answer should be 0. 0, 0, 0, 0, 0, 0, 1, 1. Only the last two come out to be 1. Fairly simple sort of truth table population. Right, let's, if you can help me and call out what is D1 equal to. Right, D1, what is the first line? Yeah, first line? 0. Next line. 0 again. Yeah? 0. Second line. 1. I'm relying on you. If you get it wrong, then this answer will come out wrong as well. Right? 0. Next line. 1. Next line. 1. Next line. 1 again. Last line. 0 can't be 0. It has to be a 1 if we 0, yeah. Is it a 1 or a 0 for the last line, guys? D1. It's a 0, right? So, guys, let's see by show of hands. How many of you got for, I'm pretty sure we're confident about Z, we're confident about D2. How many of you, by show of hands, have got a same answer for D1? Same answer for D1. Okay, so some of you guys at the back, same answer for D1, independently done. All right, so that's verified. So now we are almost finishing the table. Now, this is where, so up till now, if you really think of it, we haven't done anything new apart from how you structure your table. First, you have your system input. Then you have your current states, current or present state. Then you have your flip-flop inputs. Then you have your next or future states. Then you have your system output. I've structured it in a very strategic manner, right? You could mix it up if you want, but it makes life difficult. There are people who would go and put your system output right over here, but I've done it in a strategic manner, right? And the part of this table, this is the state table, remember. State table is an extension, is an application of the truth table. The part of your state table which you treat like your input is this side here. All right, now we bring this out. All of you should have one each of this. And I want you to bring it to every lecture. All right, we'll be using this a lot. So up till now, these three columns, we solved it using basic knowledge which we've done in week 2 and week 3. Right? Let us now look at next state and future state. Now, tell me, what table do you need to refer to? What table do you need to refer to if you know your input and you know your current state, but you want to predict your future state? Which table? Characteristic or excitation? Characteristic table. You know your current state. You know this, right? You know your input into the flip-flop, this input, flip-flop input. You know your flip-flop input, you know your current state, you want to predict what will be the next state. So let's now do that. So this is where, in order to fill these two columns, the next state, you need to refer to flip-flop tables. Or if you, it's good you memorize it, in fact. Right? Okay. So you come here. Which flip-flop are we using? We're using the D flip-flop, right? Okay, D flip-flop, and you know, okay, so sometimes what people do is they draw a small flip-flop characteristic table right over there so they can refer straight in, all right? Okay, you can do that if you want. All right, now let's look at Q1 star. Q1 star is the next state of flip-flop D1, right? Okay, Q1 star. You got Q1 as 0, you got D1 as 0. So come here. Q is 0, D1 is 0, Q star will be 0. Okay. Q1 current state is 0, D1 input is 0. Input, flip-flop input is 0. Again 0, 0 will be 0. Q1 current state is 1, D1 is 1. 1, 1. Let's come here. Let's come here. 1, 1. Q star will give you 1. All right? Look at the table I'm referring to. It's the characteristic table. All right. Let's now go to the fourth line. Q1 is 1. The flip-flop input D1 is 0. Right? Okay, see that? Look at where my fingers are pointing. 1, 0. So we come here. D is 1, right? Sorry, 0. 0, 1, right? Q is that. So you get an answer of 0. Let's go to the next line. Q1 is 0, D1 is 1. Q1 is 0, D1 is 1. It's this line here, right? So you have an output of 1. Next line. Q1 is 0, D1 is 1. Q1 is 0, D1 is 1. Output is 1. That's like just like the earlier line. Next line. Q1 is 1, D1 is 1. 1, 1. 1, 1 gives you 1. Again, Q1 is 1, D1 is 0. I think we did this early on. Q1 is 1, D1 is 0. Output is 0. Right? Okay. So I showed you how we use the table. Now, let me show you something which we wrote yesterday when we were talking about D flip-flops. Can you see here in your table, it gives you a formula. it gives you a formula. So D is one of the easiest ones that you will do. Look at the formula. What does the formula say, guys? It says that Q star is equal to D. That's the blessing about the D flip-flop. Q star is equal to D. If you look at the JK flip-flop, that's a very complicated thing, right? So Q star is equal to D. How do we know this? Look at your Q star column and look at your D column. Isn't that a match? Right? That's a perfect match. So you can say Q star is equal to D. And we did this yesterday when we did our lectures. So for Q2 star, we don't really need to go through the table, especially with D flip-flop. We can just jump in and, and just look at this. Here. Q2 star is equal to D2. Yeah? Q2 star will equal to D2. So we just copy. Done. Your state table is done. Right? Your state table is done. Okay. Okay, so these are your categories. I want you to take note of how we structured the table. I might even ask you a question. Please write down the title of your state table. Right? Okay? So this is important. The structure is important. All right, now, step 3. There's one more step to go, guys. Step 3 is something known as the state diagram. State diagram. Okay? State diagram. Now, all these things are again, in digital electronics, absolutely everything is the same piece of information being rewritten in another manner, right? I always use the example of orthographic diagram, isometric, and all this kind of thing. When we did truth table, Boolean expression, they're the same thing. If you look at the characteristic table, and then you look at the excitation table, it's just the same information. We've just flipped it around. We took this input, we put it that side, we take that output, we write the equation at the bottom. It's the same thing. All right? Okay? What else did we do? When we looked at early on, when we were doing combination logic, we had truth table, we had sum of products, product of sums, Carnot maps. All these things, they are the same information, just written in a different manner. Sum of min terms, product of max terms, same thing. Right? So state diagram is another way to visualize. So we've been introduced to state diagrams. If you look at this, this is a state diagram. This is a state diagram of so this diagram pretty much gives you the behavior of both these tables. Right? It's the same information, just rewritten or redrawn, you may say. All right? Okay, let's now draw the state diagram. Now, firstly, let's look at our problem. How many flip-flops? 2 flip-flops. How many states? 2, at any point in time, there are only 2 bits being stored. So there are how many possible states? 4 possible states. 4 possible states. Right, so let's do this. You draw something like that. 0, 0, 0, 1, 1, 0, 1, 1. 4 possible states. Okay? Now, what exactly am I trying to show over here to you guys? Well, the 4 possible states are in respect of, I'll put it down over here. That is Q1, Q2, Q1, Q2, Q1, Q2, Q1, Q2. Only 2 flip-flops. Each of them have 1 state each, but the number of possible states is 4. So it's like looking at your excitation table. There was only 4 possible lines. Okay, now, so that's our starting point. All right, let's now look at this. 0, 0. So we come here. We come here. 0, 0 becomes what? Becomes 0, 0 when input is 0 and output is 1. Okay? 0, 0, when you supply it with the input 0, system input 0, not flip-flop input. There's something known as system input, there's something known as flip-flop input. 0, 0, if you supply it with input 0, becomes 0, 0. And the output is, system output is 1. That's how we do it. So 0, 0 stays the same when x is equal to 0 and y will become 1, z will become 1. All right? See what I've done? 0, 0. I'm just putting this table in a diagrammatic fashion. 0, 0, you feed it with a 0, x 0, will become, from current state, you look at the next state line, will become 0, 0. So it stays the same place, so it loops into itself, and the output, system output is 1. Let's move to the next one. 0, 1, 0, 1 becomes 0, 0, right? If you feed it with input of 0 and output is, system output is 0. So 0, 0, 0, 1 becomes 0, 0. 0, 1, 0, 1. Oh, here it is. So 0, 1, right, moves to 0, 0. 0, 1 moves to 0, 0 when you feed it with input of 0 and output is 0. Okay? All right? Now, next one. 1, 0. 1, 0 stays the same place. 1, 0, no movement if you feed it with a 0, but output becomes 1. 1, 0, no movement. That's how you draw no movement, right? And if your input is 0 and output becomes 1, that's how we write it, 0/1, input/output, okay, input/output. Now, 1, 1, 1, 1 becomes, 1, 1 migrates to 0, 0. Input being fed is 0, output, resulting output is 0. 1, 1 moves to 0, 0. 1, 1 moves to 0, 0. Input being fed is 0, output is, what was it? 0. Okay. So notice I have written a 0/0, input/output, okay? Input/output. So that's x/z. Okay? All right, now next one. 4 more to go. 0, 0 becomes 1, 0 if input is 1, output is 1, and output becomes 1. 0, 0 becomes a 1, 0. Input is 1, output is 1. 0, 0 becomes a 1, 0. Where is that, guys? 0, 0 becomes a 1, 0 if input is 1, output is 1. There we go. All right, next one. Next one. 1, 1. Sorry, where were we? Here, 0, 1 becomes a 1, 0. Input is 1, output is 0. 0, 1 becomes a 1, 0. Input is 1, output is 0. 0, 0, 1 becomes a 1, 0. Input is 1, output is 0. 0, 1 becomes like that. Okay. Now, next one. 1, 0 becomes a 1, 1. Input is 1, output is 1. 1, 0 becomes a 1, 1. All right, last one. 1, 0 becomes a 1, 1. Input is 1, output is 1. Set. Was that correct? 1, 0 becomes a 1, 1. Input is 1, output is 1. Right. 1, 1 becomes a 0, 1. Last line. 1, 1 becomes a 0, 1. Input is 1, output is 0. 1, 1 becomes a 0, 1. 1, 1 becomes a, what is it? 1, 1 becomes a 0, 1. Is that correct? 1, 1 becomes a 0, 1. Input is 1, output is 0. Okay. 1, 1 becomes a 0, 1. So we have, again, can you see we are recycling this? 1, 1 becomes a 0, 1. How do we do that? It loops this way, right? And we have input is 1, output is 0. Guys, that's our final answer. That's our final state diagram. So all we're doing is, remember, what was the question? We are analyzing. We are analyzing the circuit. Okay? Analyzing the circuit. So this is a system. It has got 2 flip-flops. And what are we doing? We are analyzing this circuit. So this week and next week, what we will be doing is, we will be doing analysis and design in tandem. So today's lecture will be analysis, one lecture will be on analysis, one lecture on design, because it has got to go hand in hand. Design is the other way around. Okay, what is design then? Design is you are given a state diagram, or you are given the state table, and you're required to find the circuit. You're required to come back and find the circuit, right? And the purpose of finding the circuit is so that you can build it and make it work in real, right? So somebody says, hey, it should be green light, then orange light, then red light, then back to green, right? So that's the word problem. Then you've got to draw the state diagram to state table to Kano maps, equations, circuit. From the circuit, then you build, right? So that's the direction. So tomorrow we will be doing a design problem, and if you have time, we'll do another analysis problem. But in the meantime, I want you to study, see how I've done the problem, right? It's simple. It's not too hard. All it was referring back and forth. Okay. So this is going forward. Analysis is moving in one direction. Design is same thing, but moving in the reverse direction. All right. Okay. Thank you, guys. So tomorrow we'll, so please make sure you attend the lecture tomorrow and encourage your friends to attend the lecture as well. Okay, and we'll continue with this. Everyone here received a copy of the, has everyone received a copy of